Hello and welcome you all to this course on Standard Model of Particle Physics, and in this course we are going to focus mostly on the electroweak interactions with a bit of QCD also. The idea of this course will be to equip you to be able to write the Lagrangian using symmetry principles and write the interaction terms and then calculate different possibilities of the cross sections and decays, mostly involving the electroweak interactions. And I am also hopeful that this will also help you to kind of tackle some of the recent problems in physics beyond the standard model after the course. Okay, with this brief introduction, let us get started, and what I am going to do that I am going to share my iPad notes for these lectures. The first thing that I am going to do is to write the references for you. So, the first reference that I quote is actually Modern Particle Physics by Mark Thompson, and this is a very nice book, recent book, and a bunch of my classes will actually follow this book. The next book is a very classic book called The Introduction to Elementary Particles, and this is by Griffiths, and once again there are beautiful chapters and some of which I am going to follow. The next book is called Quarks and Leptons, an introductory course, and this is a classic book on particle physics by Halzen and Martin, and we learned particle physics mainly from this book. The next book is a recent book once more, but it is also a very beautifully written book, an introductory course on particle physics by Professor Palash Pal. I am going to focus at least one chapter from this book. Then I also quote some of these books on quantum field theory because that is what we are going to need it. And the first book is called An Introduction to Quantum Field Theory by Peskin and Schroeder, and this is a very classic book, and we sort of read this book for learning quantum field theory. The next book that I write is called Quantum Field Theory for the Gifted Amateurs, and this is by Lancaster and Blundell. This is a recent book and it is absolutely fantastic to read, and I suggest those who will be studying quantum field theory for the first time to kind of get this book. The next book that I quote is also a recent book. It is called Quantum Field Theory and the Standard Model by Schwartz, and this book is also very nicely written. It has a lot of topics covered, and I am going to follow a few parts from this book. Okay, so what is the main question or the goal of doing particle physics? The question is what the universe is made up of. Now, the early observation basically tells you that there are essentially four different kinds of things that we see around. One is water, the other is fire, the air, and earth. This was also mentioned in the Greek mythology. Now, if you look into the Hindu mythology, we also came up with the similar kind of idea which was given in the term called Panchabhuta. So, for example, Kshiti, Up, Tej, Marut and Vyam, these are the Panchabhuta which this universe is supposed to be made up of. So, what is Kshiti? Kshiti is earth, Up is water, Tej is fire, Marut is air, and Vyam is a new concept. It is kind of depict emptiness or ether, whatever that you, Mahakash some people say. Now, the first scientific attempt to answer this question that what this universe is made of was actually given by this famous attempt of writing all the elements together by their properties, and it was done by Mendeleev around 1869 in what we call the periodic table, right. So, in this table we know that there are this hydrogen, helium, nitrogen, oxygen, blah blah blah, then there are this sodium, potassium, the metals, and then there are radioactive elements and so on and so forth. So, all the chemical elements are arranged by their properties. And what is the basis of this organization? This basis is mainly how to describe the elements, and we know that this is described by, if you call this an X, the nucleus is mainly characterized by two things. One is called the mass number. The mass number basically tells you what is the total number of protons and neutrons present in the nucleus, and the atomic number, which is denoted by this Z, and that tells you how many protons are there actually in the nucleus, and that mainly characterizes the properties of that kind of elements. And it is very easily understood that these are not fundamental constituents, of course, because the classification is based upon how many protons and neutrons are there in the nucleus. So, therefore, this definitely constitute the universe, but these are not fundamental. So, the question is, what are the fundamental constituents of nature? Now, in order to reach to the answer of this question, there was a series of experiments for a huge long period of time, and which spans essentially from atomic, molecular to nuclear physics, and then to the present form of high energy physics. One of the first endeavors that I should mention about this was actually by the Rutherford. So, it is the famous experiment where actually Rutherford used alpha particles to hit the gold foil, and he actually observed that many of those particles are actually just passing through, a few are getting reverted back and few are getting scattered at a different angle, which gives rise to this famous atomic model. And it was way back in 1909, and I think this is the first endeavor of searching what are the fundamental constituents of this universe. And of course, from that day, from 1909 to the present day experiment which is currently running, which is called the Large Hadron Collider at CERN, Geneva, it is a long journey that we have traversed. But in this long journey, what are the scales that we have come across, or what are the notions that we have built up? So, the first thing was the revelation of atom, which we just talked about from Rutherford's experiment, and it actually probes the distance scale of something like 1 angstrom, which is actually 10 to the power minus 10 meters. Now, if we look closely into the atom, we know that there are electrons around, but there is importantly a nucleus around which this actually goes on. So, distance at which we need to probe to kind of understand the nucleus better is of the order of 10 Fermi, and that is actually of the order of 10 to the power minus 14 meter length scale. Now, when we talk about the length scale, parallelly we also have to talk about the energy scale that we are probing. So, for example, in atomic physics or atomic or molecular physics, when we are probing these atomic distances, which are also called the solid state physics, we are essentially required an energy of the strength of electron volt order to probe this kind of physics. When we want to know more about the nucleus, then you know the length scale is of the order of 10 to the power minus 14 meter, or you know what constitutes the nucleus is proton, which has a length scale, or we need to probe the length scale of the order of 10 to the power minus 15 meter to probe them, and this constitutes what we call the nuclear physics, and the energy scale at which this is probed is actually of the order of keV to MeV range. Okay? And then finally, we also know that these protons are also not fundamental particles, rather they are constituted of what you call the quarks, and in order to probe the quarks, we need to probe the distance scale as small as 10 to the power minus 18 meter, and this constitutes the realm of what you call the fundamental particle physics, and the energy that you actually required is of the order of MeV, GeV to TeV energy scale. And as we can clearly see, the smaller distance that we want to probe, we need higher and higher energy, and that is precisely why that this realm of physics is called high energy physics. Okay? All right. So, now the next question is that what is the present form of the standard model of particle physics, which actually gives you the building blocks of the visible part of the universe? What are the elementary particles and how do they talk to each other? That is the question. But before we talk about the particles, let us actually take a glimpse into what are the 4 fundamental forces that we know of so far. The first example is of course gravity. Now, from our day-to-day experience, the first force that we could come across was actually gravity, because when we drink water, it actually goes to your mouth and does not go other way, right? Then the next force that we know of is electromagnetic force, of course, and you remember this famous endeavor of Maxwell, who actually said that electric and magnetic forces are not different, but rather they are manifestation of a same force called electromagnetic force. Okay? Then there is another force called weak interactions, and this weak interaction is something which is responsible for beta decay, which we are going to talk about in a moment. And lastly, the other force that we actually have is what we call the strong force, and this strong force is the one which binds the nucleus together. Now, interestingly, if you look into the strengths of these different fundamental interactions, they are widely different. For example, if you take the strong force to have a order 1 strength, then the weak interaction has a strength of 10 to the power minus 6. Electromagnetic interaction is actually 10 to the power minus 2, whereas the gravity has a strength of 10 to the power minus 38, which is way below than these 3 others. And also, interestingly, that gravity and electromagnetic forces have infinite ranges, so they have this classical manifestation. There is a classical analog. So, for example, we all talk about this GMM by R square law in gravity, by which you can talk about the stellar motions and so on. So, that is actually risen because this force is infinitely spread. So, we had a classical analog of this force description, and the same thing is true for the electromagnetic forces. But on the other hand, the weak interaction and the strong interactions, they are actually short range. So, therefore, quantum mechanics or quantum field theory rather is essential to describe them. Now, in the standard model of particle physics, we basically have electromagnetic weak and strong interactions, and we have no place for gravity. And as you can imagine, just because its strength is much low, so therefore, it is not also very significant. Okay? So, now let us come to the description of what are the particles which constitutes the standard model. Now, essentially the matter content of these particles are divided into 2 categories. The first category is called quarks, and there are 6 of them. One is called this up, there is this down, there is this charm, there is S for strange, T for top, and B for bottom. Now, all these particles, these quarks, and how do you classify the quarks and leptons into 2 separate categories? Because quarks take part in what you call the strong interactions, so they hadronize and form baryons, whereas the leptons do not take part in strong interactions, so they therefore do not constitute the baryons or the hadrons. Okay? So, that is the main distinction between the quarks and leptons. First question that we would like to ask, that what are the intrinsic angular momentum or spin associated with these different quarks. So, the point is these are all fermions, that means they possess a intrinsic spin of half units. Now, you must tell me that what was the classification of these fermions and bosons? This come actually from the quantum statistics, right? So, the distributions are different for fermions and bosons. So, fermions possess half integer spin, while the bosons actually possess integer spin. So, up, down, charm, strange, top and bottom, everybody are fermions or spin half particles. Now, just because they form baryons, they can be assigned a baryon number. Now, it turns out that 3 of these quarks can actually form one baryon. The easiest example is a proton. So, the proton is essentially constitutes of U, U and D, okay, 3 quarks. Now, if I write a baryon number therefore for these individual quarks like 1 by 3, 1 by 3, 1 by 3 of all of these, then you can see that the baryon number for the proton will actually come to 1, right. So, if each has baryon number of 1 by 3, then the baryon number of proton will be 3 into 1 by 3, which is actually equal to 1. What will be the lepton number of these quarks? Of course, these are not leptons, so the lepton number associated them will be completely 0. So, let us write 0. And then there is another important credential, which is the electromagnetic charge. What are the electromagnetic charges associated with them? And interestingly, these quarks have fractional charges, like up quark has plus 2/3 of charge, down quark has minus 1/3 of charge, charm has plus 2/3 of charge, strange has once again minus 1/3 of charge, top has plus 2/3 of charge, and bottom has once again minus of 1/3 of charge. Okay? And you know how this charge is actually justified? Once again, let us take a look into the proton. You remember the proton is constituted mainly of U and D, and we know that the electromagnetic charge of proton is actually 1. So, now you see that if you multiply 2 into 2 by 3 and subtract 1 by 3, this is turning nicely to be equal to 1. So, the fractional charges that we assign to the up, down, and similarly for other quarks will nicely describe the charges for the baryons and hadrons that they construct. Now, if you look into the masses of these quarks, so for example, up has a mass of 2.2 MeV, down is a little heavy 4.7, charm is way heavier 1.27 GeV, 95 MeV for strange. Top is the one which is the heaviest fundamental particle, matter particle. This has a mass of roughly 173 GeV, whereas the bottom has a mass of 4.2 GeV. There is a interesting thing that you can actually see is that the first two, up and down, this has least mass, then this charm and strange has a little heavier mass, and top and bottom they have actually they are the heaviest ones, and these are usually assigned with 3 families. Up and down forms the first family of quarks, charm and strange they form the second family of quarks, and top and bottom they actually form the third family of the quarks. Now, after the quarks, let us come to the leptons. Now, the first lepton that we all know about is essentially the electron. Okay? And once again it turns out that all the leptons are spin half or fermions. Okay? So, electron has a spin half. The next is a neutrino, it is called the electron neutrino, it also has a spin half. Muon is another lepton. Now, this is something that we do not come across that often, but it is observed in the cosmic rays. There is a neutrino corresponding to muon also, so this is called muon neutrino, and there is this tau, and there is finally this tau neutrino, and all of these particles are actually fermions or spin half objects. Okay? All right. And what will be the baryon number? Of course, these do not form baryons, so the baryon number will be identically 0. Okay? So, for all of these particles, the baryon numbers will be identically 0. All right. So, what about the lepton numbers? Of course, we assign a lepton number to electron, and that is +1. So, each one of them will have a lepton number of 1 unit. So, every one will have a lepton number of 1 unit. What about the electromagnetic charges of the leptons? Now, we all know that electron has an electromagnetic charge of -1 unit. Neutrino does not possess any electromagnetic charge, so it is 0. Muon has a electromagnetic charge once again of -1 unit, muon neutrino has 0, tau will have a electromagnetic charge of -1 unit, and tau neutrino will have 0. If you look into the masses, once again the electron is 0.5 MeV. So, this is the mass of electron. Electron neutrino is almost massless, but it poses a very tiny mass. So, that is one of the issues of standard model, that how exactly these neutrinos actually acquire very tiny but finite masses, but that is a different problem. So, muon has all the properties similar to electron, but it has a mass which is slightly heavier, and it is of the order of 105 MeV. Once again the muon neutrino is almost massless, and the tau is once again heavier than both muon and electron, and the mass is of the order of 1.77 GeV. Okay. So, once again electron and electron neutrino, muon and muon neutrino, tau and tau neutrino, these are organized into different families, and this electron neutrino constitutes the first family of lepton, muon and muon neutrino constitutes the second family, and tau neutrino constitutes the third family. What is left? Importantly, there are particles which are called gauge bosons or the force carriers. Now, what do I mean? What I mean is that in quantum field theory, it turns out that every force which is mediated between two particles are actually mediated by a particle itself. For example, electromagnetic interaction is carried by a particle called photon. Okay? Similarly, the weak interaction is carried by two particles which are called W and Z bosons. Okay? And strong interaction is carried by particles which are called gluons, and you see that Gi, there is a superscript that I am using where I can be 1 to 8. There are 8 gluons that we have. Why 8 gluons? We will briefly discuss later. But for the first important point here is that all these forces have a mediator, and these are particles. And these particles have particle-like properties. Like for example, photon has an intrinsic spin which is actually 1 unit, and that is why this is called a vector boson. Okay? It is a boson, but it is a spin 1, so therefore it is a vector boson, and the same status is actually for the W and the Z bosons and gluons also. So, all the force carriers which are called gauge bosons, why this name gauge? We will come to that in a moment. These are actually bosons, these are all vector bosons rather, having intrinsic spin of 1 unit. What about the baryon number? Of course, these are neither baryons nor leptons, so we can put 0 for both baryon and lepton number for all these vector bosons. What about the charges? Interestingly, photon is a particle or mediator of electromagnetic force, as I just said. It actually relies on or talks to particles which has electromagnetic interaction, but it itself does not possess any electromagnetic charge. So, photon does not have any electromagnetic charge. W plus minus have actually charges plus minus 1, as it is clear from the way that I am writing W plus minus. Z does not have any electromagnetic charge, and similarly gluons also do not pose any electromagnetic charges. Okay? Let us talk about the masses of these particles. So, photon is identically massless, whereas if you look interestingly, this W plus minus and Z, the carriers of weak force, they are both massive, like they have masses. W has mass of 80 GeV, Z has mass 90 GeV. Gluons are once again massless, it has 0 GeV mass. The last constituent of the standard model is what we call the Higgs boson. Now, Higgs boson is a particle which was actually discovered very recently at the Large Hadron Collider in the year 2012. And perhaps many of you have heard the story that it is a fascinating journey of identifying a particle like Higgs, what does it do, and then discovering it at the collider. We will describe this in detail, so stay tuned to the later lectures, but let us first talk about its properties. Now, Higgs boson is the only boson or only particle which have intrinsic spin 0, that means it is a scalar. And there is once again, these are neither baryons nor leptons, so the baryon number and lepton numbers will be 0. The electromagnetic charge associated with the Higgs is also 0, and the mass of the Higgs boson, as we have measured, is actually of the order of 125 GeV, and this actually completes the list of standard model particles: the quarks, leptons, gauge bosons and the Higgs boson. And here we once again remind you that the standard model of particle physics does not include gravity. Now, there is also this point which you may know, or rather you may have come across from different literature in the internet, that scientists are still kind of debating upon what can be a consistent quantum theory of gravity. There are some examples people have come up, like string theory, loop quantum gravity and so on, but we are not going to talk about any of them. For us, the strength at which these particles talk to each other actually have the dominant contribution coming from either strong or electromagnetic or weak interactions, depending on what kind of interactions the particle can talk through. For example, there is one point which I forgot to mention, is actually about the leptons. See that when we talk about electrons, it has electromagnetic charge of 1 unit. So, it is of course talking via electromagnetic interactions and also weak interaction. But when we talk about the neutrino, it does not possess an electromagnetic charge, and so therefore this also do not have any electromagnetic interaction. So this can interact only via weak interactions. So that is why neutrinos are very elusive particles, and we are going to spend some time with these particles also. But the bottom line is as follows, that the standard model successfully describes the visible particles and their interactions via strong electromagnetic and weak interaction. The question is essentially how do they do so, and this is the point that we are going to deliberate upon in this particular course, right. In order to answer this question, let us first briefly recapitulate that when we are talking about the day-to-day physics, like the train is accelerating, etc., it is beautifully described by Newton's second law, rather, P equal to mf or F equal to ma in whatever notation that you want to write. This is described by what you call the regime of classical physics or classical mechanics. Now, if we have to probe the smaller distances, for example, if we have to describe the hydrogen spectra, then this classical physics does not work anymore. We have to rely on statistical physics or statistical interpretation or wave function, etc., and that is what is described by quantum physics or quantum mechanics. On the other hand, when we want to talk about particles which are moving very fast, then the classical physics also departs and we require what we call relativistic mechanics or relativistic physics. And when we want to describe those which are both small and at the same time moves with relativistic speed, that brings us to what we call the quantum field theory. So, as we can imagine that for the fundamental particles which actually are tiny particles with masses very small which can moves very fast, but at the same time they have to be described by quantum physics, we require both quantum physics and special relativity or rather relativity, and that gives you what you call quantum field theory. So, the standard model of particle physics therefore requires the knowledge or the construction of what we call quantum field theory. Now, what is quantum field theory? I am not going to spend a lot of time on this, but let us briefly introduce the basic ideas. So, it first says that every particle and every wave in the universe is simply an excitation of a quantum field that is defined all over space and time. So, this is true for all the particles that we talked about, like all the leptons, all the quarks, all the gauge bosons, the Higgs bosons and so on. So, the next point is, as we just talked about, that quantum field theory is basically a marriage of special theory of relativity and quantum physics. And the third, which is also a phenomenological need, that if we are just sticking to quantum mechanics, we cannot create or annihilate particles. In order to do so, we really have to go into the construction of quantum field theory. Now, as we understand that the basis of quantum field theory is the definition of a field, I ask this question now, that what is a field? We say that a field is a machine that takes a position in space-time and outputs an object representing the amplitude of something at that point. Okay? So, for example, how do you define the space-time? We are going to come to that in the next lecture. So, let us assume that the space-time point is described by a quantity which is called x mu, okay, where this mu is an index which takes values like 0, 1, 2, 3. That means x mu has 4 different components, x0, x1, x2 and x3. What is x0? x0 is basically time, x1 is x, x2 is y and x3 is z. So, this is the space-time point. Now, what we are going to do, that we are going to have this x mu which is a field point or space-time point, and then supposedly we are actually passing it through a field generator and generating a number or a vector or a tensor at the end of the day, and let us call that phi of x mu, which is a function of that space-time. So, if it is a number, then this is called a scalar field. If it is a number with vector, that means it has also directionality, then it is called a vector field and so on. So, as I just said, that this can be a complex number, vector or tensor as well. And there are plenty of examples that we have classically come across, for example, electric or magnetic fields. So, these are there and these are examples of fields. It takes the space-time as an input and gives you a number or a vector at the end of the day. Before we end this lecture, let me also talk a little bit about some weird units that particle physicists love to use, and this is what is called the natural units, in which this fundamental constants like h cross is equal to c is equal to 1 is actually assumed. Now, what does it mean? It makes first the expressions much more simplified. You do not have to write your h cross and c every now and then, so makes the expression simplified. More importantly, what it does, that it actually helps you to write the units of different quantities in terms of the same energy unit. Okay? Let us take a quick look. So, for example, the unit of C is basically the unit of L divided by unit of T, right? So, therefore, if you assume that C is equal to 1, that means the unit of L is actually given by the unit of time, correct? On the other hand, what is the unit of H cross? You remember the famous uncertainty principle that delta x, delta p is actually of the order of H cross. So, the unit of H cross is essentially the unit of momenta and unit of length scale. Now, if this is equal to 1, that basically means that the unit of momenta is inverse of the length scale, correct? What is the unit of momenta? Unit of momenta is unit of mass into unit of velocity, which we have assumed to be equal to 1. So, therefore, you can say that the unit of mass is inverse unit of length scale in this natural units, correct? Now, let us look into this point that E, what is the E? If you remember Einstein's equation, E is equal to mc square, which we all know. So, therefore, the unit of energy is related to unit of m and unit of c square, and if you take c unit to be equal to 1, then the unit of E will be unit of m. So, therefore, this actually allows you to express first of all the masses in terms of energy units, and this is what you may have noticed when I was writing all the masses for these fundamental particles. We actually used this MEV or the GeV units, which are in principle energy units, but used for the masses to in the natural units in the H cross equal to C equal to 1 case, right. So, this is a interesting part, and this also helps you to write the lifetime of a particle, the cross section of a particle, everything in the energy unit, and some of these exercises we are going to do in the tutorials. Okay. So, with this I am going to stop here now, and I am going to come back in the next lecture with special theory of relativity and talk about Lorentz invariance. Okay, stay tuned. Thank you.